This is Jack Jackson again. We're continuing to look at conic sections and especially focusing on how transformations relate to them. Uh, the last couple of videos we looked at an introduction to conic sections, and we looked at ellipses and hyperbolas, which if you write them out in expanded form, something like a form like this, they are they have a non-zero x squared and a non-zero y squared term. So they're quadratic in both x and y, second degree in both x and y. Now we can sort of make a actually in some ways simpler version here that is called a parabola by making sure that it's quadratic in x or y, but not the other one, linear in the other one. In other words, you only have either x squared or y squared, but not both. Okay. For the moment, we're going to assume that the xy term is not there. Kind of like we discussed before, if there's an xy term that's not zero, then it's been some kind of rotation. But if there's a zero xy term, all of these conic sections have a vertical uh, and or horizontal line of symmetry. In the case of hyperbolas and ellipses, there were two lines of symmetry, one vertical and one horizontal, that met at the center. In this conic section parabola, there's only one line of symmetry. And you know, this is actually one of the first examples of functions that you probably looked at. Probably looked at linear functions first, and probably the very next one you may have looked at, or early on at least, would have been y equals x squared, which is what you have graphed here, right? 0 squared is 0, 1 or negative 1 squared is 1, 2 or negative 2 squared is 4, so you got 2, 4, 2, negative 4. 3 or negative 3 squared gives you the same thing. It's 9. So it's here and here. So you can see the symmetry about the um, vertical line x equals 0. That is the y-axis. So we can think of that as our sort of base model. And um, then you want to take this and replace basically y by replace y by y divided by a. So now you have ax squared. Well, instead of calling it a, I'm going to call a 1 over 4p this time. I'll explain why in just a minute. But in any event, when you're changing the value of p, we're doing a vertical stretch or compression. And if p is negative, it's been flipped over the x-axis. So we do that first, and then we can do hk to uh, um, translate it, say, to the right and say up. Okay? And so that is, in general, that's going to be a parabola. All parabolas are just transformations of y equals x squared. Okay? Other shapes, some people will see a shape that's somewhat like a parabola, like y equals x to the fourth, for example, but it's not actually a parabola. A parabola is a very specific type of geometric object. We'll actually talk about what that geometric property actually is. The geometric property is that you have a point and a line. Let's go to Let's go to 1 here. Let's see. Yeah, let's do that. And so we have a point here and a line. And then what we have for the parabola, the geometric definition is that if you take any point on that parabola and you take the distance to the focus, that's the given point here that we sort of start with, and we take the distance to that line, which of course that means the shortest distance to the line, which is the perpendicular distance. Notice what happens. Those are the same number. Now we move this over here. It's a different number, but it's the same these are the same as each other, even though it's a different number than this distance and this distance. But notice no matter where you put it, those distances are the same. So this line down here that sort of generates it is called the directrix. So you have a point, the focus, and the directrix, and the distance from any point on the parabola to the focus is the same as the distance from that point to the directrix. So in particular, that means the distance from the vertex to the focus and the vertex to the directrix, that's the same distance. In this case, it's 1. Well, we're going to call that distance P, okay, and we're going to give it a sign. P is positive if it's going up, and then negative if it's going down. So if it was -1, it's going to be going down from there. So down, going down for the focus and up for the directrix. Okay, and if you do that, then this coefficient here of the x squared term is going to be 1 over 4p. Okay, so notice if I put in the one I started with was I put in 1/4, 0.25, and then 4 times 1/4 there is 1, so this is just 1. And we started with y equals x squared. In this case, it's been shifted as well, but translated. So there the focus is 2, P is 2. So there we can see that distance. Now there is a nice geometric property here. Really nice reflective property is that if you take light, let's say, or sound that's coming in, let's say it's light, coming in this way parallel to this axis. Then when it hits the, let's see, do I have the, yeah, I can show the tangent line here. So when something's coming in parallel here, it hits that parabola, it will bounce off at an angle equal to it makes with this figure, that is with the tangent line. So if you notice something with the tangent line, the angle that this vertical makes with the tangent line is the same as the tangent line makes with the line or line segment going from that point to the focus. So what that means is any light coming in here, whether it's here or over here or over here, where's it going to bounce off of? It's going to bounce off and come back to the focus. Can you see how that might be useful? Well, this is the principle behind, say, a radar dish or satellite antenna. You put the receiver right here at the focus. You build this dish, sort of a 3D, say spin it around 3D version of it, and everything that's you know, whatever waves we're measuring, uh, it'll come in here and bounce and come into the focus, and then we'll pick that up better. Or reverse it. If you're coming from the focus out, like say you put a light source here and it comes out here, it's going to reflect off and go straight ahead. Well, that's used for headlights or flashlights. So the light source is at the focus. You have a reflective surface coated with a reflective mirrored surface here on the surface of the parabolic surface, and it hits and it bounces the light straight forward. So that kind of is a geometric property of what's going on, a reflective property. Okay, well, what would the equation of this guy be? Well, we start with y equals x squared. We replace y by y actually times 4p. So this will be 1 over 4p here times the x squared. Then you replace x by x minus h to give your horizontal shift. The p changes that distance from the focus to the vertex. And if it's, of course, if it's negative, it goes down this way. Degenerates at p is 0, of course. Okay. And then we finally replace y by y minus k. Here I've solved for y by adding k to both sides. And that gives you your, of course, k gives you your vertical shift. Now, what if you switch the x and y? Well, that's going to give you just reflected over the y and y equals x, and that's going to give you a parabola that opens this way, left or right. If p is positive, uh, and the square is on the x, linear on y, then it's going to open up. And if p is negative, it's going to open down. And similarly, if p is positive, then the square is on the y and no square on the x, it's going to open right. And if p is negative, it's going to open to the left in the situation where the square is on the y and the x is long. Notice I always, however, associate x with h with x, and k with y. And again, p is the distance from the vertex to the focus. Okay, I think that covers parabolas fairly well. If you rotate these so that you do not have a vertical and horizontal axis of symmetry, then you're going to end up with a term where the xy term is not 0. I don't want to actually get into that too much at the moment, but just to say that that does happen, but it still will be a quadratic type of a polynomial. Okay, I think I'm going to stop there, and we're going to cover just a few more summary things in the next video.